Okay, here we are on page 4, and these are a continuation of the applications problems. Most of these we're not graphing them. So we're going to do number 6, and the first thing I did was I took this and I typed it into y equals. Here it is right here. And since we don't have to graph it, I'm going to look first at the table, and it asks us to write down the initial number of bacteria. Remember, the initial number of bacteria is when time equals 0, not time equals 1. So x equals 0, we look at x equals 0, and we see that the y value is 5.17. So that would be the initial amount of bacteria. 5.17. Then it says to find the local maximum and minimum number of bacteria. And to that, for that, we're going to have to look at the graph and do second calc max and min. So we'll graph it. Oh, remember we did that last problem on the last page. Let's go back to Zoom Standard, which is how it is when the calculator is turned on. Negative 10 to 10, negative 10 to 10, and there is our function. Let's see, I don't see the top of the maximum point here. So what I'm going to do is I'm going to change the window a little bit. I'm going to make it go from 0 to 100 because we don't want the negative part. Oops. 0 in x min, 100 in x max, and then y min and y max I'll make it go from negative 10 to, I don't know, 100 also. And then I'll graph. Okay, so it looks like we got a local max there and a local min here, and then it goes up. Does it curve again? We know that it doesn't, because we know there's only 2 turning points maximum in a cubic function, and there's a max here and there's a min here. So let's find the max. Second calc max, which is number 4. The left bound will place it slightly to the left of the maximum point. Then we'll hit enter. Oops, I hit enter twice, I guess. Oops, I need to do the right boundary here. So let's redo that. Second calc max, which is number 4, and then left bound, okay, enter, and then we're going to move the right bound cursor slightly to the right of the mountain, hit enter, guess, we just hit enter again, and the maximum appears to be 15.2, comma 13.2. And the minimum, let's do that. Second calc, and minimum is 3, and the minimum is this valley right there. So we'll put the left cursor there, the left boundary there, and we'll put the right boundary here. Enter, enter. And the minimum is going to be 32.96, so 33.0. And the y value is 10.9. Okay. State whether this is a suitable model or not and justify your answer. So this is a model for the number of bacteria. And here x is in minutes, okay? It says that in 100 minutes, let's look at the second table and we'll look at what happened after 100 minutes. After 100 minutes, it's 360, and goes up quite a bit. Again, just like the last time, okay, bacteria probably in a petri dish can grow to, a huge number, I don't know, thousands or millions of bacteria. But eventually it's going to get to the point where the petri dish or the human or whatever is hosting the bacteria is going to be at capacity, and then the bacteria is not going to grow at that, huge slope anymore. And so it should level off. And so that's what I would say is maybe why it's not a suitable model. It may be a suitable model here, but why doesn't it level off at the end? Okay, so a cubic model is not capable of making it level off because we know it shoots off to infinity. So again, not ideal for like biology problems. Okay, number 8. The temperature, x degrees Celsius over a 24-hour period beginning at 7 p.m. on Monday evening is represented by the function blah blah blah, where t is the number of hours that have passed since 7 p.m. State the highest and lowest temperatures in this 24-hour period and find the temperature at 5 a.m. On Tuesday morning. Okay, so let's type that in to Y1, and I will do that offline and come back in a sec. Typed in this function in here. How confusing that the function is called x, and the output usually we call it y in the calculator. So the input value is t, so the t becomes x, and the x actually becomes y. Okay, where t is the number of hours that have passed since 7 p.m. So at 7 p.m. t is 0. At 8 p.m. t is 1. At midnight, which is 5 hours later, t equals 5. Okay. State the highest and lowest temperatures in this 24-hour period. Again, the graph is probably the best place to look at that. Whoa. It got cold, didn't it? It went below 0 degrees here. Let me adjust the window so that we can see a little bit lower. So instead of -10, I'm going to put -100, and I'll graph it again. Okay. All right, so it looks like I have kind of like a minimum here and a maximum here. So let's find that first. So we'll find the maximum first, second calc max, which is number 4. And oops, I hit the enter too soon. The left needs to go over here, and the cursor was over here when I hit the enter for left. Let me go back and do that one more time. Second calc 4, which is maximum, and then I go a little bit to the left so that I am on the left side of the mountain. Then I hit enter, and then I go to the right side of the mountain. And then I hit enter, and then I do guess, and the answer is 18.2 for the highest point. That's the time. So 18 hours after 7 p.m. is when it reached the highest temperature, and the temperature happened to be 24.7 degrees. Okay, that's the highest. And then the lowest looks like it was very close to time equals 0. So let's find lowest by doing second calc min, number 3. And then we'll move the cursor all the way to 0. And then we'll hit enter. And then we'll move it a little bit to the right. And let's see where the minimum point is. The minimum point is 5.63 hours after 7 p.m. That's close to midnight. Remember, 5 was midnight, slightly after midnight. And the temperature is 19.2. Okay, that was the lowest. Okay, now find the temperature at 5 a.m. on the Tuesday morning. The easiest way to do that is on the table, right? Or you could do trace 5, I guess. So I'm going to go back close to x equals 0. And I'm going to find out what the temperature is at 5 a.m. 5 a.m. is how many hours after 7 p.m.? Well, 7 p.m. till midnight, remember, is x equals 5. So 5 a.m. is 5 hours after that. So 5 a.m. is actually 10 hours after 7 p.m. Okay? So I'm going to look at 10, x equals 10, and the temperature is 20.7. And the x value, remember, is 10. Okay? So in this case, the answer I'm looking for is 20.7 here, and the highest and lowest temperatures, the answer are these two. Okay, you don't need to give the ordered pairs. I'm just giving that to you just in case you'd like to know what the time is that those temperatures occurred. Regulations state that a hospital should be at a maximum temperature of 22°C. If the temperature rises above this, the air conditioning system should be switched on. Assuming that the temperature in the hospital is the same as the outside temperature when the air conditioning system is off, find the number of hours over the 24-hour period during which the air condition must be switched on. Okay, so we're just concerned with the 24-hour period. So you know how I made the graph go to 100? We actually only need to make the x max to be 24, right? Okay. All right. Okay, actually it never went to 0 degrees Celsius then, okay. So we're actually going to find the hours now where the temperature was above and below 22 degrees. So in order to do that, I am going to adjust the window so that we don't need so much y. The y min doesn't need to be negative. It can be 0. And the y max is never going to be more than 35 degrees on Earth, hopefully. So I'll put like 50 for the y max, and then I'll graph again. And then we are going to compare it to 22 degrees. It's hard to see 22 degrees on here. The easiest way to do it is to put y2 to be 22 degrees. And then when we graph it, we'll see the two compared to each other. And then it says, find the number of hours during which the air conditioner must be switched on. So what if we found this intersection point and this intersection point? Then we would know what time it was above 22, what time it was below 22. I'm not sure if it intersects here too. We could try that. We could look at that intersection point here. Okay? So we'll find those 3 intersection points. So we'll find intersect, which is number 5. And the first curve is the cubic, we say yes. The second curve is the straight line 22, we say yes. And then we move the cursor close to the first intersection point here, and we hit enter. And we got 0.981. So I put, and so for the first intersection point, the first intersection point is 0.981, comma 22. The second intersection point, second calc, intersect number 5. First curve, second curve, guess. And we need to put the guess closer to the second intersection point if we want to know what the second intersection point is. The second intersection point is 12.0, comma 22, of course. Okay, and then the third intersection point. Okay, sorry, I had a technical problem and I had to restart my work, but here we are, we're back again. I need to adjust my window again. My window, if you remember, x equals 0 to 24, and my y value is 0 to 50, right? So 0 to 24, because we're worried about the first 24 hours. Y min, y max would be 0 to 50 because it is summertime and it's not going to go below 0 here. Graph. And then remember that I had the second function at 22, and I'm finding the intersection points so that I know when those times are. And so like I already found this one and this one, now I'm going to find the third one. I find the third one the same way, second calc intersect, and then I move the cursor close to the third intersection point, we hit enter, and then first curve, second curve, guess. And then I hit enter again, and then it tells me that the answer is 22.7, comma 22. You notice the y values are all 22 because the intersection points of a line that is always at height 22, of course, are going to be 22, right? Even though the curve is varying, the straight line is always at height 22, so any intersection points on that straight line are going to be at height equals 22. Okay, so assuming that the temperature is the same as the outside, find the number of hours over the 24-hour period when the air conditioner must be switched on. So the air conditioner must be switched on when the temperature is higher than 22, which is between these 2 points, right? Because look, it would be from here to here. That's when the temperature goes higher than 22. So what I'm going to do now is I'm going to take the 2 times, 22.7 and 12, and I'm going to subtract them because I want to know the number of hours during which the air conditioner must be switched on. So it would be 22.7 minus 12, and that would be part of the answer. It would be 10.7 hours. And then also we should look at the 0.981 because do you see how it went up and down like that? And 22 degrees was here. So basically anytime you're above 22 degrees, which is here, And here, you need to count that time. So from 0 to 0.981, we also need to count that. So 0 to 0.981, the length of this time, or the duration of that time, is going to be 0.981 itself. And then if I want to add those two together, basically I'm going to get something like 11.7, right? And so, and I can do that on the calculator to confirm, but 0.981 is basically 1. And then 1.0, right? And then when I add it to a 10.7 is 11.7. So the number of hours given your answer in hours correct to one decimal place is 11.7, okay? Comment on whether this model would be useful to predict the temperature in the hospital at 1 a.m. on Wednesday morning. Okay, 1 a.m. on Wednesday morning. Well, actually, you know, if what they're asking is, oh, could we just take this model and, you know, basically 1 a.m. on Wednesday morning, what X value or what T value would that be? Well, 7 p.m. on Monday is going to be 0, right? And so Tuesday at 7 p.m. is going to be 24. And they're asking, what about Wednesday at 1 a.m.? Wednesday at 1 a.m. is like 6 hours after Tuesday at 7 p.m., right? That's 6 hours later. So that would be t equals 30. Well, let's see. If we looked at this function at t equals 30, first let's look at the table value to see what value the function would be at t equals 30. See if it's a reasonable number. It is 0.7. So it would be almost 0 degrees. If we remember that when we looked at the graph before, we can look at it again here. Just we'll change the window to 30. Remember that the cubic function just goes to, oops, actually we want it to be, we want the x max to be 30. Okay. So the cubic function necessarily has to go to negative infinity, positive infinity. These 3 points are the intersection points that we found, and right after it hits 24, the thing just goes to 0. So this model is not good for predicting anything past, you know, Tuesday at 7 p.m. So no, it's not good because obviously it's not going to go down to 0 degrees the next day, because I think we're talking about the summer since we're using the air conditioning. Now, how could you use this model? Well, what you could use this model for is, like, you could say, okay, I'm going to cut this off because I know that, you know, past x equals 24, the thing is worthless, but temperature cycles kind of repeat. And so you could, like, take this and then take this model and then, like, translate it to the right and then repeat it over and over again. So you could use this model as a basis to figure out Wednesday at 1 a.m. Or you could say, oh, what I'm going to do is to figure out, to predict what the temperature is at Wednesday 1 a.m., I would look at Tuesday 1 a.m. or, yeah, Tuesday 1 a.m. And Tuesday at 1 a.m. is basically 6 hours after 0, so it would be t equals 0. So you could say, okay, I'm going to look at the table. I'm going to look at x equals 0 or x equals 6, and that would be, oh, not 6. It would be, yeah, it would be 6. So t equals 6 would be 1 a.m. on Tuesday, and it's 19.17. You could say, oh, 19.17 is a pretty good estimate for 1 a.m. on Wednesday also. Okay? So, yeah, it depends how you use it. You could use this model to try to figure that out, but you couldn't just, like, plug in x equals 30 and get the answer, because that, we could see, will give you almost 0 degrees Celsius. Okay, so I think that's it for this page. Yeah.